Okay, so many thanks for the invitation. You know that I hesitated quite a bit before accepting the invitation, but it was not because I didn't think this would be a great workshop. I knew from the beginning it would be great, and it is great. The only thing is that recently I've been having trouble finding enough time to write things down, which is one of the reasons why this is work in progress, which maybe it shouldn't have been, maybe it should have been finished. We'll try to finish it as soon as possible. Okay, so it's two parts. I give two parts, and then Nick gives the third part. Yeah, so let me start by telling you what a stochastic flow is, which you may know. So we have a probability space and a measurable space, and then you can have a stochastic flow on this measurable space. This is a collection of maps from the space into itself for each time s and t real times, one less than the other. And the minimal condition that you would want is that this whole joint map is measurable. Usually you want something more, so continuous sample paths, whatever, you can get to that. And the main thing you want then is the flow property. These operators should have these maps should have the property that if you first go from S to T and then you apply the map from T to S, you get the map that goes from S to U straight, right? And from S to S, that's the identity map. And these are random maps. So that's a stochastic flow. And sometimes this is relaxed in the sense that this thing holds for fixed deterministic times almost surely, and it may not hold really for all times at the same time. Although ideally you would have it like to have it in this strong form. Then some extra definitions. You can say that the stochastic flow is stationary if shifting all the times doesn't change its distribution, and you say that it has independent increments if these are wrong. There should be this type of x's. If the maps that get you from one time to the next and then the next to the next for disjoint time intervals are independent. And I'll say that it's independent increments. And if you have such a stochastic flow and you pick some real time and then a random variable in your space that is independent of your flow, then you can construct a process by starting with this random variable and evolving it for time t, starting out at time s. For each t, this gives you something, and that is always, that is, if now you have independent increments, then this is a Markov process. That's a very general thing. And if this is stationary, then it's a time homogeneous Markov process. And you have all undoubtedly seen this many times, because very often when you construct a Markov process, you actually do more. You do a sort of pathwise construction, and very often gives you actually a stochastic flow. So we've seen many Poisson constructions already in the last 2 days, and they typically give you a stochastic flow. Also, if you have a diffusion process, but you construct your solutions as solutions to some SDE driven by a Brownian motion, that also gives you a stochastic flow. And in general, if you have a stochastic flow, you get a little bit more than, because you get a natural coupling of processes started in different initial conditions. So you can, instead of just taking one initial state, you can take n different possible initial states. You have a random variable in this space, and you can evolve each of them under the same stochastic flow. And that also gives you a Markov process. And that gives you a natural coupling, and that is often very useful between these individual Markov processes. And these coupled Markov processes, then you call the endpoint motions of your stochastic flow, and they are in a natural way consistent. And there's this paper in Annals of Probability by Lejean and Raymond from 2004, where they have actually studied quite generally consistent families of Feller processes. And they show that each such a consistent family gives rise to a stationary stochastic flow with independent increments. The only thing is that they had to choose this weak form of the second thing. And then there are certain conditions, there are technicals that I will not say, but there is a certain if and only if there in that paper. And we will be interested in a very special type of stochastic flows, namely those stochastic flows where the space is the real line and the endpoint motions are non-crossing. So that one motion cannot cross over to the other, or alternatively, that means that these maps, they are monotone. So if you start below one other, you stay below the other one. You cannot cross. So one example of such a stochastic flow is the very well-known Arratia flow, and then the endpoint motions are coalescing Brownian motions. So here you see them. Here you see all the points. Here you start with a whole real line, and it's mapped to various times here, and you see all the points where it's mapped to. So it coalesces very quickly. So here the whole real line is mapped only to this locally finite set. and that gets smaller and smaller because here you see a coalescence. So that's the Arratia flow, and it's clearly non-crossing. That's one example. Yeah, we've also seen these sort of pictures in Sandra's talk, actually. So this is a way to approximate this Arratia flow with a discrete thing. So you can interpret this as a map. So here you have the even integers, here you have the odd integers, and these arrows, they give you a map from the even to the odd. And here you have a map from the odd to the even, and so on. You can concatenate these things. You get something like a discrete time stochastic flow. And if you then rescale things, you rescale space by a factor epsilon and time by a factor epsilon squared, and you send the epsilon to 0, then you think that in an appropriate way, you should converge to this Arratia flow. And one of the interesting questions is, what is an appropriate way? How should you formulate it? And that is exactly what these talks are, one of the things that we are going to talk about. Yeah, but I want to give you a few more examples of monotone stochastic flows. So another example are Harris flows. So a correlation function is a function from the real line into the -1, 1 interval that is continuous. In 0, it's 1. And it has the property that if you pick finitely many points and you construct a matrix like this, that matrix is positive semi-definite. And then there is a theorem, Bochner's theorem, that you may or may not know, that tells that if you have a symmetric probability measure on the real line and you construct its Fourier transform, that is a correlation function, and vice versa. Each correlation function arises in this way. Okay, so that's an important one. And now Harris in 1984 showed that if you have such a correlation function, then you can use it to construct a consistent family of endpoint motions, which are defined by a well-posed martingale problem. So the generator then looks like this. So you sum over all x and y, you take this rho and then the second derivative. And yeah, then you have to have to get uniqueness of the solutions to the martingale problem, you have to impose an extra condition, namely if two paths coalesce, they meet, then they coalesce. That's the extra condition you need. And with that extra condition, it's unique. It depends on this rho whether you need this condition. There is an integral condition that tells you whether these paths actually meet. So if this is finite, then they meet and you have to impose that condition. If this is infinite, they don't meet, so you don't have to do anything.
I find this extremely interesting. I mean, no Gaussianity in the beginning holds, so that comes, but this is a Gaussian process.
Yeah, it is Gaussian. It is very Gaussian. And so the endpoint motion, the single motions are actually just standard Brownian motions. And the endpoint motions are correlated Brownian motions. So if you look at the flow, it's most easy to formulate. So if you look at, you start with the point x, you evolve it for a small time t, and you say, what is the displacement? And you look at the covariance with a displacement at the point y, t to 0, tends to 0, this limit is exactly this. So it's the sort of the correlation, this rho really gives you the correlation. And this strange condition about that it has to be positive semi-definite has to do with the fact that you're sort of constructing a high dimensional Gaussian and you want the covariance matrix to be non-negative definite. You can't have negative things, otherwise it wouldn't exist. So that's why you have that sort of strange condition on this rho that is an if and only if for this process to exist. Okay, so this is fairly abstract. So let's see a concrete example how you can get such a thing. So this is an example that motivated actually. This is where Nick and I more or less started. So here we have endpoints. So for the moment, it's really finite here. You have endpoints here, and in each time, so here you have n even, then you have n odd, and so on. You alternate. So this point, yeah, and you should do it periodically. So, say this point here on the left is the same as this one. That's how you should read this picture. And then in each step, you choose 2 points at random from this sort of discrete circle, and you cut the circle up into 2 intervals. And in the one interval, you draw all your arrows to the left, and the other one, you draw them all to the right. And you do that for each interval. Well, that's basically it. And that gives you something that looks very similar to the picture we had before. but this time, so you can extend it. Another way to do it is not to do it to do periodic boundary conditions, but to extend it. Just take this picture and copy it here and here and here, and also on the left to extend it to the whole real line in a periodic way. That's to get into the framework of Harris, who works on the real line. Then you rescale like this with n and n squared, and you get a limit, and that is a Harris flow with this particular correlation function you can check. So you see there is now really a correlation. If you're very close, then in each step you have a very big chance to be in the same interval, so you're really correlated. And you can check that you get exactly this Harris flow. But this is a periodic function. Now it is one not only at 0, but also in the points 1 and 2, which means that's because it's periodic, you're fully correlated. If your distance is exactly 1, then you will stay completely correlated. Actually, you can check that this correlation function is positive definite if and only if this constant here. It could be as much as 6, and then it stops being. And I should say not every Harris flow has such a nice approximation. If you would want to remove the 4 here and put a 6, then I wouldn't know any nice discrete model that converges to that. So similar. And this particular one actually has to do with these flows of bridges. In one of the papers of Bertrand Legal, they usually work on the unit interval, but they have at some point they also work on the unit interval with periodic boundary conditions, and they show that this particular one is related to the Kingman coalescence. Okay, so these are two examples of monotone stochastic flows whose underlying endpoint motions are continuous, and if in fact a single one is Brownian motion. But you can also do discontinuous things. So to define that, let's define for each a and b real, let's define a function which has that you map x to a if it lies between a and b, either in this or that order, and otherwise you just stay where you are. So if a is less than b, the function looks like this, and if a is bigger than b, the function looks like this. And now you can try to make a stochastic flow that works in this way, that you pick some. Oh, this should be a b. Sorry, no, this should be a. Sorry. You look at all pairs a, b, where a is different from b. So you remove the diagonal. And then you put a locally finite measure on that. And then you construct you take the product with the back measure, and you construct a Poisson point set on pairs A, B plus times. And then the idea should be for each point in your point set that looks like this, you apply this map at that time. And you can try to do that. It will not work for every locally finite set, but under suitable conditions, you can hope that this sort of gives you a stochastic flow, which should again be monotone. So it looks like this. I mean, you can this would be A and this would be B. Here, this would be A and this would be B. So you have some sort of Poisson set, and if you then construct the motions here, you lie in this interval. So you go to this point A and so on, and more. If you have more of them, it looks like this. So it's some sort of you get Lévy processes. You can even try to do it in an alpha stable way. But they can't jump over. If this one tries to jump over the other one, then it actually coalesces with the other one. So you do preserve the order. So this is also something that we found interesting, and we want to include in our general setup. Okay, so this is sort of the general idea. So we want to go to stochastic monotone flows on the real line, and possibly with jumps. And we want to apply ideas that have so far been developed only for this Arratia flow. So for the Arratia flow, you have a beautiful theory of the Brownian web, and I'm going to recall to you what that is. So let me first do the picture. I mean, before I said that the Arratia flow was about coalescing Brownian motions, and then the endpoint motions is just, you start endpoints on the same time level, and then you evolve them, but you can also start at different times. So you can define stochastic coalescing Brownian motions started at different points in space and time. I mean, the idea is here formally, like you can write down it formally, like you have a collection of points. You have for each point, you have a Brownian motion independent Brownian motion starting at this point. Then you lay down your first one. And then for the second one, or for the ith one, you look at you stop your second one as soon as it hits the place where you've already been, and then you continue as the first one. And then the third one, you stop it as soon as it hits this set where you've already been, and then you look which one you've actually hit, and you follow that path, and so on. That's formalized here, but I think the idea is clear. And this is nicely consistent. And this is then the basic construct from which you construct a Brownian web as follows. So you have a space of continuous upward paths, and you equip it with a suitable topology. And I don't want to say what topology yet, because we're going to do it more generally for paths with jumps, and this is going to be one of the main topics of the talk. But for the moment, let's say there is a nice topology on this space. Roughly, you should think of the topology as you want the starting point, the starting times to converge, and you want the paths to converge locally in a uniform way. And then you can construct coalescing Brownian motions from these countably many points. And you can choose these points so that they're actually dense in the whole plane. And you can then take the closure of the set of all these paths in this space of paths, and it gives you a compact. Then there's a theorem by Fontasi, Newman, and Rapishanka that gives you a compact set of paths in the right topology. And the construction doesn't actually depend on how you choose this dense set of starting points. And this thing is then called the Brownian web. And again, that is now you have actually a good way to formulate this. I said before that you have this discrete approximation of the Arratia flow. Now you can formulate it in terms of webs as a convergence. So now you have your space of paths, and then you look at all compact subsets of that. And there's a natural metric on this, the Hausdorff metric. It's nice to be able to talk about this here in this institute. And we also give the data later. And then you have this arrow configuration that also defines you sort of a collection of coalescing random walk paths. You rescale that. And that's a compact set of random walk paths. And if you rescale it, then it converges in this space with this topology weakly to the Brownian web. So here you have a very nice concept of convergence. So that's one advantage of this web formulation. Okay, so tell you a bit more about the Brownian web. So if you have, we've seen this picture with the black ones already before, and then you can draw dual white ones that go down. So that's the dual web. So this is the odd sublattice, and these things are drawn in such a way that they don't cross the black ones, and it's unique. And that also has a limit. So how to formulate that? So if you have n coalescing Brownian motions starting from finitely many points, so going up, then you can also define downward Brownian motions starting from the same points. And then if you meet one of the upward paths, you reflect of it. So let me use the blackboard ones. So the idea is that first you lay down your finitely many coalescing Brownian motions in forward directions, but this all goes up. Well, actually, that should be black, and now the next picture should be white. But that doesn't work so well. And then the dual paths from the same points, they will just be Brownian motions. So well, it could happen that they hit actually one of the paths that go up. And then you have a Skorohod reflection. So it's an immediate reflection of it. And then these things, of course, they coalesce and like this. And the remarkable thing about this is that this is actually consistent, and also it's symmetric. Which if you forget about the white paths, then suddenly this reflection is not visible, and these red paths are just Brownian motions, which is first very surprising if you just see it like this. But if you think of it as the limit of what we've just seen, you understand why that is true, actually, and that is actually how it's proved. I think there is no direct proof of this. There's only proof via discrete approximation of that. It's in a paper by Balin Todt and Wendelin Bernard, I think, that they studied. No, yeah, Sokaluk. Yeah, I'm wrong. Sokaluk and the Todt wasn't there. That's I missed. Sorry. Yeah. Okay, so then you have, because it's consistent, you can then use Kolmogorov to extend, and you can do it even for countably many, such a collection, forward and backward from these points. And you can take the closure of the forward path and the closure of the backward path. That gives you two things. And one is a forward Brownian web, and the other is a dual Brownian web. And they don't cross each other. But you can also do another thing that you can do is you can actually concatenate these paths. You can take this one plus this one together, you get a bi-infinite path, and you can look at all these bi-infinite paths and then take the closure, that gives you something that's called the full Brownian web. Okay, and all these objects we will try to sort of generalize later. So this dual picture, as you see, is quite important. It's also very important for understanding the structure of the Brownian web. So, so at a typical point, if you just pick one point in the plane, and with probability 1, there's just a single path going up and a single path going down. But then there are these random points where there are actually 2 paths going out or 3, and you can understand these with the dual picture. If you understand the dual paths, you see that the number of dual outgoing paths equals the number of incoming paths plus 1, and the vice versa. And in this way, I will not go through the details, but I want to say that this whole dual picture is quite important for understanding the structure and also the structure of the flow. So this brings me sort of to the end of part 1, which is to state really what is the aim of our work. So our aim is to extend this theory of the Brownian web to more general stochastic flows with non-crossing endpoint motions, including ones that make jumps. Good. So now I have 20 minutes, right, still, and then more. Okay, so this is part 2, and now we'll get to real maths. Because so far it was a bit. So now I will go to the real. It will be a lot of topology, actually. It's more topology than probability in a sense. So, okay. So we want to do cat-like functions and have topologies on these. And let's first tell you what I mean, you all know what a cat-like function is, I suppose, right? Continuous with left limits. But let's do it slightly different way. So let's define a split real line. So this is a set that consists of pairs. You have a time and a sign. Sign can be plus or minus 1. And so this is one way of writing it down as t plus or t minus. Another way of writing, sometimes it's easier to have just a single notation for such an element. So I will call it then, say, tau, an element of the split real line. And then I will tau underbar will be my notation for the real part. And S of tau will be the sign. So this is how I think. That is my notation. And you can encrypt this space with the lexicographical order, which means that 2 of these. Okay, so you have split every element of the real line. 2 this split, such a split real number is less than another one. If either the real part is strictly less than the other one, or if they're equal, then the sign should be ordered in the nutshell. So the minus is less than the plus, of course. And then you can work with the split reals as if they were reals in many ways. You define sigma strictly less than tau if it's less or equal and not equal. And you can define intervals, half open, closed, half open, as you would be used to. Well, actually, it's true if you do you define it in the usual way. This is actually open. This is closed. But there is a bit of the redundancy. I mean, some of the things are actually both open and closed. I mean, this interval, for example, is the same as this one. So this one is actually also closed, you can easily see. And yeah, I mean, the whole thing, because you have split everything up, actually, it's totally disconnected, right? You've disconnected everything from everything. Okay, this I also use for half infinite intervals. I use the obvious notation as well. Okay, once you have this, okay, what I say with open, well, it becomes true if I define a topology on the split real line, and I do that by choosing the order topology. And by definition, the basis for that is formed by all intervals of this form. So now it's by definition, these are open. And if you define it like this, then you have a convergence criterion that says that a sequence of split reals converges to something of the form t plus, even only if the real part converges to t, and eventually you're above this thing. So in this order on those things. And likewise, you converge to something from t minus if the real part converges, and eventually you're below it. So it's a way of, the convergence must always converge from the right side to go to the t plus or to the t minus. And so as a topological space, you can check that this thing is first countable. It has the Hausdorff property. We have him again here. It's a separable space. It's not second countable, and it's not metrizable. So that's the slight thing, that it's a bit ugly in that sense. But for compacts, it's again okay. So a set is compact if and only if it's sequentially compact, if and only if it is closed and bounded. So these are things you know from the reals, and they're still true. They're even true if you have this to the product with itself. So you can prove. So in many ways, it's still a very decent topological space. And now you can say, okay, I have an interval in this split real line. I have some Hausdorff topological space, and I have a function from the interval to that space. When is that continuous? That's continuous if and only if ftn goes to ft plus for all tn that go to R. So the real part goes there, but it's now enough to have it strictly bigger than t. So, and likewise from the left. So you see that a function from the split reals to something else is continuous if and only if, if you can now define f plus t of a real. So you can define now a real function, or a function on the real line by taking t, adding a plus, and then taking the f of it. And you can also define a function on the real line or an interval of the real line by first taking the real number t, then adding the minus, and then taking the f. And these two functions, the plus one should be Catlak, the minus one should be the other thing, like left continuous with right limits, and one should be the Catlak modification of the other. That's basically it. So you see that actually Catlak functions are just continuous functions, but on a somewhat unusual space. And this is not a new observation. Actually, when Skorohod published his paper in around 1950 about Skorohod topology, Kolmogorov also wrote one paper about it, and he immediately made this observation, actually. So yeah, maybe not as detailed as here, like he didn't prove all these properties of this thing. And actually, this split real line is very similar to things that people like Urison were working around 1910 on. The ideas are very old, but it's been a bit forgotten. And for example, if you now have a function, so you take, so this is an interval of the subreal line. So I take 0 plus up to infinity. So for all real positive real numbers, I take the minus and the plus version, but for the 0, I only take the plus one. I don't take the minus one. And I have a continuous function on that. Then the plus part is Catlak, and f minus is its Catlak modification. So this is typically what you need in Markov processes, of course. If you would also include this 0 minus, then you would get something very similar to what you know, but a bit different, because now it would be actually possible that f minus, that the function makes a jump at time 0. But usually, in the usual definition of a Catlak function on the half line, you can't jump at the initial time, right? So here you can actually be more precise. You can choose to allow that by using this interval, and you can choose to disallow it by choosing this interval and allow it by using this interval. So this formulation has a bit of an advantage that you can be a bit more general than usual Catlak. I mean, usually these problems are only at the endpoints of the interval, so it's hardly worth the trouble. But once you start working with paths which have different intervals and you want to reverse time, then the Catlak is of course also not symmetric. So it's in the end it gets pretty ugly. And this is actually a very good, it's mathematically probably the most beautiful way of looking at Catlak functions, although usually you don't need to do it. Okay, so that's one ingredient we'll need. Another thing I want to tell you about is squeezed space. I think we've also seen this already, right? So this is nice. That, so if you can take the real line, so you can take the real line, the plane, you can compactify. So here space is horizontal, time is vertical. You should think of it that way. That's in most of the pictures. So first you compactify in the space by adding plus minus infinity. And then you also want to compactify in time, but you want to do it in such a way that if time is plus or minus infinity, you don't care anymore about your spatial position. So instead of having here a whole interval of possible places where you could be at time infinity, you squeeze that all to a single point. For the reals, that's nice to do, and but you can actually do it for a general. If space can here actually doesn't have to be the reals, you can do it for space being a general metric space. So for general metric space, I define a squeezed space, which is the product of that with the reals. And then I add 2 points at a time plus and minus infinity. And that space coordinate I just call star, where star is some element that is not part of the original space. This is going to be the extended reals. This is some metric on the extended reals that generates a topology. I choose some function that is continuous, strictly positive on the reals and 0 at the end points of the reals, extended reals. And I can define now on this squeezed space, I can define a metric in this funny way. And you can check that this is a metric with the property that now you converge in this squeezed space, if and only if the time coordinates converge in the extended reals. And if the limiting time coordinate is real, then the space coordinates must also converge. But if this thing is plus minus infinity, you don't have to converge. So you don't care where you are if time is plus minus infinity. It took me actually quite a while to find out that actually for a general metric space, you can define this. There is a small proof that this satisfies the triangle inequality. This is a few lines, you have to check it. Because I mean, for the reals, you can just do it like this by this picture, you just scale. But for the general metric space, like multiplying all distances with something that doesn't really make sense, right? So this doesn't work. But this is, you can actually do this. You can define a metric on any metric space that gives you exactly the topology, the squeezed topology that you want. And the basic idea will be to have some sort of local convergence in the end, where it's near infinity, you don't care where you are. That's the idea. Okay, so and then you can prove simple things like if this is a separable space, then this is also separable. If it's complete, this squeezed space is also complete. And you have a compactness criterion set in the squeezed space is compact, if and only for each finite time. If you intersect your set with the set of points which have time coordinates in here, then it's included in something compact times that. So it's sort of locally compact. Again, it's so that's your compactness criterion. Okay, so that's the second ingredient that we need. And now we can really start to say what the path space is. So a path, so I have a general metrizable space. I have a path in that space that will have a starting time and a final time. And I want a starting time, it could be minus infinity, and final time could be plus infinity, but it should be ordered in the right way. And then I define this is the extended domain. It could be the whole extended real line possibly. And then this is the restriction. This is the domain restricted to the reals. And then this, oh, there should be a pi here, I'm sorry. Then I take this interval, the real part, and then I make all the plus minus combinations. So this is an interval of the split real line. And now I have a function from this interval to this, that is continuous. So this is basically a Cadillac function. So this is for me a path. So it's a Cadillac function. Essentially, it's like a Cadillac function on a closed interval of the real lines into X. And this, but the domain can vary. Like you can have look we need it for these coalescing Brownian motions. We need functions that have different domains, and we need to say how far they are from each other. So this is now my set of all paths. Then I have a subset of those for which P minus is T plus for all T. This is sort of the continuous paths. So they're not the Cadillac ones. Well, this is continuous always, but this is here now the real thing is continuous, no jumps. And then for the Brownian web, we use also this space where, the final time is always infinite. That's I call it like this. Yeah, these are for me the upward paths. For the dual Brownian web, we needed this space of where the sigma is minus infinite. So these are paths that are going down. Okay, and if you have now a path defined in this way, in this path space, you can always construct its graph. So this is the set of all, well, for me, the closed graph. These are the set of all pairs P, T plus minus T, where T lies in this real thing. And you also have to include these points at infinity if they're in this extended domain. And then you can check that this graph is always a compact subset of the squeezed space. So here you have a function, for example, is defined on the half line. Here it makes a jump. This is my function, my path. And here this is closed graph. So this point and this point are both included, right? Because it's not that like you usually with Cadillac, you would draw a thing like this. Here it's full and here's an empty circle, but here the closed graph, these are both points are both included. And then this is a compact subset of the squeezed space. Okay. So let me use, I think Nick has slightly different. He just calls this A, B with square. So this is the real line. This is the interval. If A is less than B, then this is the closed interval AB. If B is less than A, then it's this interval. This is my notation to to be sure that you know what I mean. Then I can define something else, which is the interpolated graph. And I'll first show you the picture. The interpolated graph of this would just be to add this part. So I now add this interior piece, which means that I now take all pairs xt, t lies in the domain of my path, and x lies in this, on the line segment between t minus and pt plus. And again, I have to add these points at infinity if they're in the extended domain. And then again, what's going on? This is not my latest version. I corrected this. I remember there's a typo here and I corrected it, but it's not here. So this second line you can forget. And this thing is a compact set, I wanted to say. Oh, interesting. Good. Okay. Hausdorff again. So if you have a general metric space, then you can define the distance of a point to a set as the infimum of all distances to points in that set. And k of x will be the set of all compact subsets of it. And k plus of x will be all non-empty compact subsets. And on that space, there's a natural metric. That's called the Hausdorff metric. And that's defined as it's the maximum distance of a point of x in the first set to the other set, and then the maximum of that with maximal distance of a point in the second set to the first set. So maybe I'll draw another picture. So if I want to, I have one set in the plane that looks like this, and I have another set that looks maybe like this. Then I can say, okay, this is maybe K2 and this is K1. So I can find the point that is furthest from the point in K1 that is furthest from K2. I look at this distance. I can find the point in K2 that is furthest from K1. I look at that distance and I take the larger. So I take this distance. That is going to be the distance between these 2 points. That's a simple, good idea of Hausdorff. Well, I don't know if it's Hausdorff, you know the rule that things are never named after the people who invented it, but he must have been close to to this if he wasn't the real inventor of this. So yeah, that's the Hausdorff metric. Another way of formulating it is in terms of correspondence. So a correspondence between two sets is a subset of the product space with the property that for each point in one, so it's a set of pairs, and it should have the property that if you have a point in one set, then there is always a point in the other set, so that the pair is in this correspondence, and vice versa. So it's like, in particular, if you have a bijection between the two spaces, and you look at all point plus where it's mapped, that's a correspondence. But this is more general in the sense that it doesn't have to be a function in, so it could be more to one, and actually it could be more to one in either direction. So it's sort of generalizing that idea in that sense. So then you can look for two sets at the set of all correspondences between them. And then it's very easy to see that the Hausdorff metric, equivalently, it's just the infimum over all correspondences over the maximal distance between a point and a corresponding point. And that's easy to see. I mean, I can just define a correspondence between these sets by mapping each point in one set, linking it to the closest here, and linking each one in this one to the closest in the other set. And I get a correspondence that gives me this, and the other direction is also easy. So this is an alternative formulation of the Hausdorff metric. Okay, so then you can again prove nice things. If your original space is separable, then the non-empty compact sets with the Hausdorff metric is also separable. If your initial space is complete, then this metric space is also complete. And you have a compactness criterion that says that a set of compact sets is compact if and only if all these sets, all the elements of it are contained in one and the same compact set. So there's a compact containment. And you have also a convergence criterion. A sequence of compact sets converges. But if you have a sequence of compact sets, you can define two things. You can first define all limits of sequences of points xn, so that xn is an element of the case thing. And for all sequences that converge of this form, all these limit points, you call that all the limit points. And then you can ask also for a bigger set. You can just ask for, maybe I have such a sequence, which the property that it has a sub-sequential limit, so it has a cluster point. I can look at all cluster points of such sequences. That's more. And then you converge if in the Hausdorff metric, if and only if this set of limit points is equal to the set of cluster points, and you have this compact containment. This is an if and only if. What is nice about this convergence criterion is that you see that actually the topology that you get from this Hausdorff metric doesn't depend so much on the choice of the metric on your original space. In fact, if I would replace this D with an other metric that generates the same topology, so that could be a very different metric, then still the topology I get from the Hausdorff metric is again the same. So actually, it's good to have a name for it. So yeah, so how do you call the topology generated by the Hausdorff metric? Well, that is, of course, the Hausdorff topology. Now things get slightly complicated. So you must be very careful. I mean, in English, you can do it. In some languages, you don't, like Czech, you don't have articles. But in English, you can make the distinction. You should say the Hausdorff topology. That's the topology generated by the Hausdorff metric. And a Hausdorff topology, as we know, is a topology which has the Hausdorff property. So that will be, and maybe that's a good point with so much Hausdorff to stop the first part, and then I'll continue after. We had the motivation. We already had quite a lot of topology. Does it work? Oh, yeah, the microphone seems to work as well. So what we had the Cadillac functions, which are actually continuous functions on this strange split real line, which is, yeah, it's mainly a tool for doing things slightly more elegant, or you can avoid it if you want, but it's really an elegant way. And one of the things that you can do with it is you can allow Cadillac functions to jump also at the endpoint of intervals, which is sometimes not allowed in the standard formalism, which will actually be also very convenient for having elegant theorems at the end. Then we had this squeezed space here, which has the idea that you don't care where you are if time is too large, which is sort of a local thing. Then we had path space, and we had a graph. This is, and we had the interpolated. Right? This we had, right, still. Oh, and the Hausdorff metric. We also had that. I went quite fast. And now we can finally start to put everything together. Yeah, this is where we are. And so now we want to, finally, I promised you all the time at the beginning, I said we have this nice space of paths, which is the one that you use for the Brownian web. And we now want to generalize it. We want to have this space of paths also with jumps. And we want to put a right topology on it. And now we have all the ingredients that we need to do that. So the first idea is that you can now you have two paths, which are functions, which can have different domains, different intervals where they're defined, but you look at their graphs. And the first thing you can, where's the graph? Here is the graph, and you can have two of these graphs, and you can just look at in this squeezed space at their Hausdorff metric distance. That would be the first idea that you could have. That could be and that really does give you a topology on your path space. And actually, this is a known topology. This is sort of the G2 topology. I mean, Skorohod has this paper, which is the one that we all use. That the important one is the G1 topology. That is now mostly called Skorohod's topology, but there are 4 topologies in there: G1, G2, M1, M2, but he of course looks only at paths that are defined on a fixed domain, right, on a fixed interval. And here we are a bit more general in the sense that the interval where they're defined can change. And the first thing you could do is look at these closed graphs, look at the Hausdorff distance. And if you do that, that gives you a metric defines a topology. And that is actually the G2 topology of Skorohod. And the other thing I said, in the particular case that this target space is the extended reals, you can also look at this interpolated graphs. And you can use the Hausdorff distance between these. That gives you a different topology, and this is actually the M2 topology. These are okay, they're good topology, but they're not so good for most purposes. And the problem with both of them is the following thing. You could have a sequence of paths that do this, where these times are very, very small, and these lengths of these time intervals go to 0. In both these topologies, that would converge to this function. But usually you don't want that. I mean, specifically, if this is a sort of Markov process, you think that the Markov process that makes 3 jumps is very different from one that makes only a single jump. So you sort of do not want to include that for many reasons. And so you then think, well, what are we doing wrong? So the thing is, I mean, this if you would do the closed graph or the interval graph, it's clear that this is close, right? This as a set is close to this. So, so what are we missing here? Well, these graphs, or the interpolated graphs, they have a natural order. There is an order on it, a total order. I mean, if you look at these graphs in here, you can walk through them in a certain order, which is basically the order in which you think you go through that path, right? So yeah, if it's a normal path, you go here, and then you go here, and you go here, and here. If it's interpolated, you also have this piece actually here. What is drawn here is interpolated one, and also that is ordered. So here it's more formally 2 points in this graph are ordered if either in this way, if either the first time is strictly less than the other one, or if the times are equal, then if this point is closer to this target at t plus than the other one, you say that it's also further. So that's the natural total order. And now you can say, okay, I want not just to compare the distance between 2 closed sets, I want to compare the distance between 2 closed sets which are equipped with total orders. And we had this expression for the Hausdorff metric in terms of correspondences, right? But now you say, okay, maybe I want, if I have an order, maybe I want a correspondence to respect this order. So maybe I want to say a correspondence is monotone if you cannot find a point in the one set, A1, and a corresponding point in the other set, and then another point, Y, in the first one, and a corresponding point in the other set, so that this point is less than that one, but the corresponding points are ordered in the other way. So if this happens, then I would say this is not monotone. If it doesn't happen, then I would say this correspondence is monotone and sort of respects the total order. And particularly if this would come from a bijection, it would be sort of like a strictly increasing function then, right? So, yeah.
Just a general question, but so if you go back to the previous slide, you were saying that J topology has this problem of not accounting for very close jumps. That's if you take the J1 topology and it's relevant.
Yeah, we're getting to the G1, right? This is G2, and the G1 is over this. I'm going to define that one. Yeah. So one thing you can do is that instead of using the Hausdorff distance, you can define a different distance, which I would call H plus. So now you take the infirm over all correspondences that are monotone in this way. So you are only allowed to find correspondences that respect the order. So that would give you a natural metric. And you can do this again for the normal closed graph, or you can do it for the interpolated graph. And the other thing, a different idea, is the following. If I have a totally ordered set, subset of X, the space X, then I can define a subset of X squared is all the pairs so that X is less or equal than 1. And now you can define your X squared space with a metric that generates the product topology. And just, if you want to compare 2 sets, you can look at these things defined this way and look at their Hausdorff distance in that set. And it seems actually that this and this metric, they generate the same topology. And this, I must say, again, it's work in progress. We have seen some I have proofs in some special cases, but I want to find out how general this statement actually is, but it's, and how it's precise. But it seems actually that both approaches give you the same topology. And this is the more standard way in the literature, so that it's closer to what you find in the literature. This is another thing that we came up with. And then actually, if you do this actually for this H plus, but for this one, I'm sure it's the same actually, that then you get exactly, this is sort of the G1 topology. It's a bit of a general thing, more general thing, because we allow general intervals, like you compare paths that are defined on different intervals, but otherwise this is, if you restrict yourself to paths on the same interval, this is exactly the G1 topology. And the M1 topology would then be the one where you don't use the closed graph, but the interpolated closed graph.
So in the web topology, when you find the distance of that state, you measure the distance between a starting point and then basically the unit or north path.
Yeah, I get, so these distinctions between interpolated graphs and closed graphs are of course only important if you have jumps, right?
But what would be wrong by just saying that?
And also this problem doesn't occur if you don't have jumps. So
what would be wrong by just saying that the distance between paths would be a combination of measuring the distance between the starting point and then just like the J1 distance between the paths afterwards. Does it work?
it's probably very similar. If you have jumps, the G1 topology is a bit nasty if you want to make it local. I mean, if you have a you have your space, say, of cut-like functions defined on the whole real line, and now I take such a function, I restrict it to a closed subinterval of the real line. That function, this restriction, is not a continuous function with respect to the G1 topology, because there could be jumps that approximate the endpoint of the interval. And this is really a nuisance, because usually if you say, okay, I have this thing and I now want to define sort of a local version, I want to have G1 convergence locally, then usually you would say, okay, then for each projection it should converge, each compact convex it should converge, but it shouldn't even converge for the projections, because the projections aren't even continuous. So this is not a way to do it locally. And there doesn't seem to be a very easy fix to that. I mean, we fix it with this squeezed space. That is actually the way to get things local.
Well, that's the point, right? Like all this space.
To get it locally. Yeah, this is one of the reasons why that is a very convenient thing. I mean, you know, the squeeze space was already in the web paper of Fontes and such. So already there, it turned out to be very useful for having compactness and such. But this is another advantage of it. Right. Yeah. So I said there's so basically you want a way to take this order into account, and then you get the G1 and M1 topologies. And the difference between G1 and M1 then, and also is that, and also for the M1, M2 and G2 is then the M topologies have the property that this is close to this, right? For the G1, this wouldn't be close. Here you have two jumps. This is really different. But here for the M1s, this is actually very close. And G1 is actually for Markov processes the most natural thing, because Markov processes have this sort of, what happens after something is sort of independent. So typically for a Markov process, good Markov process, you will not have two jumps very quickly after each other. If that can happen, then you can have many more after each other, and you usually get a mess. So it's very natural for Markov processes that you don't have jumps quickly after each other. But this M1, as we will see, actually, we will, for our theory, we will need to use the M1 a lot. And Nick will explain why we need M1 actually in some cases. So you shouldn't completely forget about it. And so you said for the web, you have these continuous functions, and then things simplify a lot. So if you look at the subset of continuous functions without jumps, that is, it's a closed subset of the whole path space except with the G1. It's not actually closed with respect to M1. But anyway, if you then, whether it's closed or not, you can always take the topology that we have G1 or M1 that you have defined here and look at the induced topology on the subset consisting only of the continuous paths. They induce the same topology. And this is also would be the same as the M1 and M2 and G2. It would all be the same thing. It would just be the Hausdorff distance between the these closed paths, basically. That would be, for the continuous things, a lot of these problems don't exist. And then sort of the easy way to describe that topology would just to say, yeah, it's like locally uniform. And there you can do also restrict. There's also no problem with the restriction map is now continuous. It's much easier. Okay. Yeah, and and now you can read, but now we have this big space which allows for jumps, and we can put either G1 or M1 topology on it. And you can prove that you actually get a Polish space. And yeah, for the G1 you get it. For the M1, it usually makes sense only for the real ones. I mean, you can do it a bit more general. You could do it on any space where there is sort of a closest path between two things. But usually, why would you have convergence in that sense? In one dimension, it's sort of natural that you have. There's only one way, one closest way, and the M1 topology is most natural if your space is the reals, actually. Okay, so the last thing I want to explain to you is about moduli of continuity. So if you have continuous paths, then you have a usual modulus of continuity. So if you have a path, well, you can define it for any path. You fix some t and a delta. So you look at all time points in the minus t to t interval, which are not more than delta. So this is the real part of us. These are split reals, but the underline means that I look only at the real part. So that they are not more than delta of each other, and look at how far you can get. So how much can the function value change if you change the time variable only by delta. And then the G1 modulus of continuity is the supremum of, okay, so this is the normal modulus of continuity. And you may know that this occurs, for example, in the Arzela-Ascoli theorem for the compact subsets of the set of compact functions. And there are similar things for G1 and M1. So I want to tell you they are a bit more complicated. So if you want to do something similar for G1, you're going to look at something else. You're going to look at 3 times. And now you say, okay, first I look at the distance between where I am at time sigma and tau, and then I look at distance between tau and rho. And I look at the minimum of them two. So that means now I can make a jump. Like I can make a very big jump, provided that right after that I do not make another jump. So this modulus if I have a path that looks like this, then this modulus, G1 modulus of continuity, will be very small. I think it's actually 0 here, because I can take first time here, the second time here, and third time here. Here I will have a big distance, but the other distance will be 0, and the minimum of them will be 0. But this would be very bad, right? So 2 big jumps straight after each other, or also like this, up and down. This would be very bad, because then you can take this 3 times, and this distance is big, and this distance is also big. So this modulus of continuity sort of is big when there are 2 jumps quickly after each other. And for the M1, you can do something again similar. Now you take 3 times, and now you want the process at the middle time to be close to this set. Remember, this was the interval from this to this, if they're ordered in this way or the other way. So it's this line segment connecting them. So that means that now you have 3 times, so sigma, tau, and rho. And here at time sigma, I'm here. At time, maybe I'll draw them closer to each other. At the other time, I'm here. And this can be a big jump. But now the value at time tau should be close to this interval connecting them. So when it lies inside there, it's okay. When it's close to it, it's still okay. But when it's further from it, then this modulus of continuity will start to get big. Okay, so we have now 3 moduli of continuity. And then we can formulate compactness criteria. Okay, so I still need something more. We say that a set of paths, we remember that the set of paths is compactly, the C, I want to generalize it more general, but the C shouldn't be there. we say that something is compactly contained if it's sort of locally compactly contained. That means that for every finite t, there is a compact set, so that on this time interval, the path stays in this compact set. And we then can call it with the usual modulus of continuity. We say that it's equicontinuous if the limit as delta goes to 0 of this usual modulus of continuity, supremum over all paths tends to 0 for each finite time. And then there is the Arzela-Ascoli theorem, here generalized to path space, that says that you're pre-compact if and only if you're compactly contained and equicontinuous in this way. And this thing has generalizations to G1 and G2. You just have to replace this modulus of continuity with the other two, and you get exactly the same statements. Here again, I should say that to formulate these theorems in this nice and elegant way, it's important to allow jumps at the initial time. If I wouldn't do that, then so if you, for example, if you only look at Cadillac functions, say on the half line, whereas usually you don't allow a jump at time 0, and you want a continuity criterion for in the G1 topology, then you actually, apart from equicontinuity and a compact containment, you need one more condition, which forbids paths from making jumps at times very close to 0, because in the limit it will give you a jump at time 0, which is not allowed. But because we allow it, this theorem actually gets better. And again, you see that it's better for the theory to do it in that way. So how much time do I have left?
8 minutes.
8 minutes, 38 minutes I give to you because I have no more slides.
So, are there questions?
Yeah.
On those diagrams on the board, a point worth making is that the two bad things that the J1 modulus allow, the M1 modulus meets one of them, but not the other.
Yeah.
So one on the left, very close in the same direction twice. The M1 modulus is fine.
Yeah, this is
One on the right, bad.
this happens in M1, but not in G1, and this doesn't go here in either one, right? That's what you want to say, right? This is the bad thing that is okay for M1, but not for G1, and this is bad for both, right? Which examples did you want to? These are the two that you were thinking about, right? These are the two. Ah, yeah, this one. Yeah, this is also bad in. This is always bad. This doesn't go here. This would be bad even in G2 and M2, because you see that this graph isn't close to this one, even if you don't care about the order. This one actually, I forgot at some time. I mean, many people must have run into this trap that they don't read the literature or it. They just go by their own intuition, and you forget that you can actually. This is what you think of, but this is not what you immediately think of. That you have to think of. Okay, that's a good. I was actually saying that it makes most sense if your space is just a reals. I mean, there are actually. You may know geodesics, right? Even in a metric space, a geodesic is a finite geodesic is just the shortest path between 2 points. It's like you map you have an isometry from a real interval into your space, so that the distance is exactly the real distance. And many metric spaces have the properties that if you take 2 points, there's a unique geodesic connecting them. This is true even for RD, right? It's just the shortest path connecting them. So in a sense, it would be this M1 actually sort of makes sense in any space where there are unique geodesics. But I must say, if I think of applications, I cannot think of any process where you would naturally converge in such a way that you would always, if you do make jumps, sort of within the approximating are really jumps, but you're very close to the shortest path. But maybe there are examples, I don't know. It is well defined.
But so, like,
now on you're developing theory for both the topologies in a way, and then depending on the applications, you will go either for one or the other one.
Yes, it turns out that we will mostly use M1 and need M1, but Nick will explain why. But I think G1 we know is extremely useful. So and because you can develop so nicely in parallel, I just definitely wanted to show you both.